In this video, we're going to look at the conjugacy classes of the alternating group on 5 symbols, A5. And actually, we're going to prove that A5 is simple, which means that if n is a normal subgroup of A5, then either n is equal to A5 or n is trivial. And so the proof of this fact and why it's related to conjugacy classes comes from a fact that any normal subgroup must be a union of conjugacy classes. So why must this be true? Well, what does it mean to be normal? It means that G and G inverse is equal to n for all G in the group. Well, just take an element in this normal subgroup. What you now see is that the conjugacy class of X must be a subset of n. Why? Because of this equality. This equality states that the conjugate of X must be an element of n for all G, and so this whole subset must be a subset of n. And so for each element in the normal subgroup, its conjugacy class is a subset. And so then you see that for every element, the whole conjugacy class is a subset, so you see that n must be a union of conjugacy classes. And since if you partition the conjugacy classes into disjoint, separate them, so separate this union, you can actually rewrite it so it's a disjoint union. Although that part's not quite as relevant for right now, but it is important later. It must be a disjoint union of conjugacy classes. So one advantage of determining the conjugacy classes of a group is that you can use it to determine the normal subgroups. Given all the conjugacy classes, you just look at unions of conjugacy classes and figure out which ones are actually closed under multiplication and inversion. Those are the ones that are going to be subgroups. So now let's take a look at A5, and let's take a look at the centralizer. So I'm going to let G be A5 so I can write G instead of A5 all the time. Let's look at the centralizer in G of a 3-cycle. So remember, odd cycles can be written as products of an even number of transpositions, so all odd cycles are in A5. So we already know that if you conjugate this 3-cycle by any permutation, you're going to get another permutation. That's just a fact about symmetric groups. Of course, that doesn't tell you that this is true for alternating groups, so that's going to take a little bit more thought. But we do know that this is true for conjugating by permutation, so it's also true for conjugating by permutations in the alternating group. What else do we know? We know that the centralizer contains the subgroup generated by the 3-cycle, and we also know it's contained in all of A5, and A5 has order 60, and the cyclic subgroup generated by 3 elements is order 3. So, ignoring the fact that this permutation has to be in the alternating group, just look at this permutation. Look, if this conjugate is going to be in the centralizer, this conjugate is going to have to give you the 3-cycle back. So we see whatever we're doing, sigma 1, sigma 2, and sigma 3 have to be permuting 1, 2, 3. And not only that, it has to be a permutation that's permuting them in cyclic order. So we see that whatever's going on, it must be the case that sigma must permute one. We have either, if you restrict to the set, well, let me say it carefully. This permutation has to fix 1, 2, 3 as a set. And so when you take this restriction to the set 1, 2, 3, we're going to end up with either the identity map, the cycle 1, 2, 3, or the cycle 1, 3, 2. We see immediately each of these is even, and so it's not too hard to see that sigma restricted to 4, 5, sigma of 4, 5 has to fix 4, 5 as a set as well. Why is that true? Well, picture. We have a bijection. And what we've just said about this bijection is that the top 3 elements must be permuted among themselves. Then it follows that the bottom 2 elements must also be permuted among themselves, or else you don't have a bijection. So we have a bijection from 4, 5 to 4, 5. There's only 2 options. Either it's the identity element, or it's the transposition 4, 5. So we see overall we only have 6 possible permutations. And you look at these 6, taking a product, one of the products here with one of the products here. But then you remember we're in the alternating group. And so we need our product to be even. And you see that these 3 permutations are already even. And so if you multiply them by the transposition 4, 5, you get something odd. So we see that there's actually only 3 elements in the centralizer, namely the 3 that are already in this cyclic subgroup to begin with. So all that to conclude that the cyclic subgroup, or that the centralizer of the 3 cycle is the cyclic subgroup generated by the cycle. So then the index of this centralizer is 60 over 3, which is 20. All right, now how many 3 cycles are there in A5? Well, every 3 cycles in A5. And how many 3 cycles are there? Well, you have to choose 3 elements to be on the 3 cycle. And then once you pick the 3 elements, A, B, C, you either have A, B, C, or its inverse, A, C, B. These are your 2 options. So you have 2 times 5, choose 3, many 3 cycles in A5. And you can check that that is the same number. So in fact, every 3 cycle is in this conjugacy class. So that's what we managed to conclude from this. So we see this took more work than in the case of the symmetric group, but we were still able to derive the same result. And it's essentially a similar proof. So now that we talked about the 3 cycles, let's look at the 5 cycle. It, of course, contains the cyclic group generated by itself, which is a group of order 5, and so This group has either order 5, 10, 20, 15, 30, 40, or 60. So this one's going to take a little bit more work, but we can try to figure it out. Of course, as noted before, if you conjugate by any permutation by the cycle, you're going to get this cycle. And if sigma is in the centralizer, then you better get the 5 cycle back. And so lining up in all the possible ways, you should see that in this case, unlike the previous case, it must be the case that you get just the cyclic subgroup. What do I mean by previous case? Well, I mean, in the previous case, you also got the cyclic subgroup, but it took more work. What I mean here is that all 5 elements already appear on the 5 cycles. So there wasn't this issue where I had to restrict to subsets and do some careful arguing. Here it's just flat out true. And why is it flat out true? Because in order for this to be true, one of these sigma i's has to be equal to 1. And then you see that sigma I plus 1 has to be equal to 2, and so on. And so you immediately see that this bijection, whatever it is, has to be given by, its inverse has to be given by sending 1 to I, 2 to I plus 1. And now you see that this operation is really just a shifting operation, that sigma inverse sends j to I plus j, modular. Or here, of course, modulo 5. I'm identifying 0 with 5. 0 with 5. So then that tells you right there that this permutation, well, what's the only permutation that involves this kind of shift? It's a cyclic permutation, a cyclic shift, and so it's one of these 5 cycles. So congratulations, it's a subgroup of size 5. And so what do we get for the index? Of our centralizer, of our 5 cycle, we get that it's 60 divided by 5, it's 12. However, how many 5 cycles are there? Well, what do you have to do to specify a 5 cycle? If you write the 5 cycles so that the 1 appears first, you have to specify the other 4 entries in 4 factorial ways. So there's 24 5 cycles. 12 is not 24. So not every 5 cycles conjugate to 1, 2, 3, 4, 5. In particular, unlike the case of the symmetric group and the alternating group, it's not the case that all k cycles are conjugate to each other. In other words, cycle types and conjugacy classes are not the same thing. So the conjugacy class of 1, 2, 3, 4, 5 has size 12, but it's not everything. And so we've gotten 12 5 cycles plus the 23 cycles so far. That's only 32 of the 60 elements of A5 by conjugacy classes. So we still got more work to go. We don't have all the 5 cycles, so we need to find a 5 cycle that's not in the same conjugacy class. And it takes a little bit of work, but you could probably see, well, let's pick a different example. How about 1, 3, 2, 4, 5 is not conjugate. To 1, 2, 3, 4, 5. Let's take a look at that 5 cycle. How can you know that this is true? Well, because remember, it is conjugate in the full symmetric group. But you can check that the only permutation that works is the one that swaps 2 and 3, and that is not in the alternating group. Granted, that part's not really that important for our argument. The important part is that there exists another 5 cycle that's not among the 12. And by the exact same arguments we just gave here, the size of the conjugacy class of that 5 cycle is also 12. So we can update our count. And so we got 44 of the 60 elements into 3 conjugacy classes of these 3 sizes. Now let's look at the conjugacy class in G of 2 disjoint 2 cycles, like that. Again, what happens when you conjugate? You're going to get sigma 1, sigma 2, sigma 3, sigma 4. It's 2 disjoint transpositions. And you want that to be equal to 1, 2, 3, 4. What's going to have to happen? Well, what are the possibilities? Either 1 and 2 swap places, 3 and 4 swap places, or they both swap simultaneously somehow. And so at the very least, you see whatever's happening, sigma 5 is a fixed point. And so sigma 5 is a fixed point, then sigma is actually in the alternating group on 4 letters, or can be viewed that way. And we already determined that the cyclic subgroup, the centralizer in A4 had size 4. And so we already know the size of this centralizer here because it turns out to be the same centralizer. And so now the index in G of this product of 2 disjoint transpositions is 60 over 4, which is 15. And so what do we have? We have 60 is equal to 1 plus 15 plus 12 plus 12 plus 20 by the class equation. These are the sizes of the individual conjugacy classes. And so if there's a normal subgroup of, suppose we had a normal subgroup in A5, that's proper, then what do we need? We need the size of n to be a divisor of 60, and we need the size of n to be sum 1, 15, 12, 12, and 20. In other words, it has to be a union of these conjugacy classes. So you have to find some way to collect some subset of these numbers and add them together and get a divisor of 60. In fact, we certainly know that you have to include this 1 because that's the identity element, and the identity element certainly has to be in your normal subgroup. So you need to have 1 plus a bunch of these other things needs to be a divisor of 60. And so, process of elimination. What happens when you add 1 with 12? Well, 13 is not a divisor of 60. If you add the two 12s together to get 24, you get 25. That's not a divisor of 60. So we see that we have to add at least a 15 or a 20. Well, if you add the 20, you at least get something that is a multiple of 3, but it's still not a divisor of 60. And you can see that if you add 12 to that number and 24 to that number, it still isn't going to work. And so then 1 plus 15, that's not a divisor of 60. If you add 12 to that number or 24 to that number, it's still not a divisor of 60. And finally, 20 plus 15, 36, not a divisor of 60. The only way to get a divisor of 60 is to add 24 to that, which gives you 60. And so the only sums that give you a divisor of 60 is 1 by itself and everything, which means that the only normal subgroups are the trivial one and the full group. As you can guess, using this type of argument to prove a group is simple in general would be way too much work, so we'll eventually use other better methods. But it's nice to know how to use something as simple as the class equation to end up proving that a group has no non-trivial normal subgroups.